Hey, in the previous video, I explained the concept of multicollinearity and full rank condition when you have one regressor. And so let's extend the idea to two regressor cases. Now suppose that there are two explanatory variables, beta 1 and beta 2, x1 and x2. In this setup, full rank condition fails or a multicollinearity problem arises if and only if one variable is multiple of another variable. So in this case, I do not include intercept because there is no intercept in this equation. So you can imagine, in this case, you may imagine the mean of x1 and x2 are 0. So if two variables have some kind of multiple relationship, so multiplication, so one variable is another variable multiplied by a constant, then the full rank condition fails. That means, as I said, when you change x1 will automatically change it. So when you double x1, x2 will be doubled. When you increase x1 by 1 unit, then x2 will increase by gamma unit. So there is no way you can handle the controlled variation. So you cannot have controlled variation when this relationship is true. And then, so that's the intuition that how can we prove that the identification fails? It's simple. Mathematical proof is to show that a counterexample. That means, suppose that beta 1, beta 2 are the true values, then I will show that there is an observationally equivalent parameter values. That was the definition of identification failure. So then suppose that I will show you that there is a different value, beta 1 and beta 2, which are observationally equivalent. How can we show that? Define. So this will be beta 1 tilde and beta 2 tilde. I know that they will be observationally equivalent when they satisfy this relationship. I'm just giving you one number, but one number is given this way. You may choose a different number, but let's see this number. Just one value will be enough to disprove identification. So now suppose that, so from beta tilde, you observe y tilde. And if y tilde is generated from beta tilde, but exogenous variables are given in the same way, so x and epsilon are given in the same way, they are given from outside. So then suppose that y tilde is generated from the same exogenous variables and error terms with different parameter values, beta 1 tilde and beta 2 tilde. But according to our assumption, we know we define those two values this way, and then beta 1 tilde was the combination of true values, and x2 had no effect. However, even if they are given this way, using this relationship, x2 equals to gamma x1, so this guy becomes x2 again. So x2 again, so in the end, this is exactly what we had. So different y tilde is the same as the original y. So this is exactly what I meant by observational equivalence. So you don't need to choose this number. I just chose one number to make it simple. But any parameter value, in more general, more formally speaking, any parameter value that satisfies this relationship is observationally equivalent. Proof is the same. It's easy to show that. So as a result, any parameter value that satisfies this relationship is observationally equivalent, so we cannot uniquely determine one parameter value. So that's how we show that identification is not possible. Do you get it? I hope it makes sense. And then let's think about partition regression or partial out formula. This is now, suppose that you have, it's a review, I believe you have learned this partition regression formula in econometrics 1. So this is also related to this case because it's basically the partial out is about the controlled variation. So suppose that we are interested only in beta 1. But so we know that x2 affects, x2 has some effect on y, but we are interested only in x1, beta 1. Then how can we simplify this? And the formula is given in econometrics 1, where P is a projection matrix. So P is a projection matrix onto x2. Sorry. So E is Korean. Actually, I'm reading the number in Korean. P2 is I'm not sure if I read those equations correctly. Sometimes, you know what? So like I think mathematical equation. So my first language is Korean. Second language is English. And maybe another second language is mathematics. Mathematical equation itself could be viewed as another language. So sometimes when I read mathematical equations, equations, I mix up Korean and English. Like for example, yi equals to something, but equals so x1 beta 1 plus x2 beta 2, but plus is said in Korean as 더하기. So sometimes I write it like I read it this way: yi equals to x1 beta 1 더하기 x2 beta 2. So if I did that, please understand. I believe you understand what I'm saying, and I'm just reading out the written equation. Okay, back to the theory. So beta 1, we are interested only in beta 1. And the idea is to project x1, linearly project x1 onto the space of x2. And then m2 is the residual. So subtract the projective value. And then this is unexplained part. So m2 x1 is unexplained part of x1 by x2. So I explained that, residual. So you are splitting x1 into a part that's explained by x2 and the remainder which is not explained by x2. And what you need is the remainder, the residual. So the residual is the controlled variation. You are moving x1 this much, you can move x1 this much without changing x2. So this part will change, always changes whenever you change x2. So when you change x2, x1 will follow this much. However, the other part, the residual, is what does not change. You can move around this guy without affecting x2. So it's orthogonal to x2. So you may move x1 without fixing x2 here. But when you move around this way, x2 will follow in the same direction. So, and when x1 and x2 are multicollinear, that means there is no residual. The residual is the only independent variation in x1 controlling x2. Then what can we learn from this formula? Assuming that you understand this formula, I can say a few things. So you can connect the multicollinearity to the projection and residual concepts. And also, when you think about one regressor case, I explained the importance of variation in the regressor. And you may apply the same idea to this case, to partial out case, because after removing the effect of x2, you may understand that the residual is the only regressor of this equation. So the variation in this regressor, this residual, the variation in this residual is playing the same role as this guy. So the variation in here is important variation is the variation in the residual. And third, why this is important? Because suppose that you have like many variables, but you are interested in only one. Then the problem here is you may want to draw a graph to see what's going on. So drawing a graph is the best way to understand what happens in the data. But when you have, say, 3 variables, you need 3-dimensional graph, which is not possible. So then the partition regression concept will help you. You would like to isolate x1 and y, and then how can you isolate them? By taking the residual after projecting onto x2. So projection residual is the isolated variations. So then after removing the effect of x2, you may use residual in y and residual in x and draw a graph and see what happens and see if there is enough variation and if there is any clear trend. So that's how you can apply, how you can use the partition regression in practice, and how you can understand, how you can connect the partition regression to the concept of multicollinearity and the importance of variation or the full rank condition. Okay, let me continue in the next video. We'll study something different. Bye.